So we discussed the idea of predicting three-dimensional structures using the VSEPR theory for species that have 2 pairs of electrons, 3 pairs of electrons, and 4 pairs of electrons. But as you know, in Lewis structures, for certain elements in the third period and beyond, they can actually form more than 8 electrons. In other words, they can violate the octet rule by having expanded octet. And for these, you're going to have additional VSEPR geometries that is beyond what we saw for those structures that follow the octet rule. So this one here is a structure that has 5 pairs of electrons around the central atom. So an example would be PCl5. And so the notation we use here is to use the central atom label as A and then the terminal atoms marked as X. So we have 1 central atom and 5 terminal atoms. In this case, we have 5 pairs of electrons around the central atom and no lone pair. So all 5 are bonding pairs. The structure you would see is shown here in this molecular model. So there's 3 bonds that are all in the same plane, and then you have one that's sticking out to the top and one that's sticking out to the bottom. So in fact, this looks like 2 pyramids that have a triangle base. The name of this electron geometry is trigonal bipyramidal. The name of its molecular geometry is also trigonal bipyramidal because it has 5 pairs of electrons, they're all bonding. Now, you can remove one of these pairs of electrons to make it so that you have 4 bonding and 1 lone pair. Now, when you remove this, there's an option, right? You can remove either the top one or you can remove this bonding pair and make it a lone pair. Well, it turns out that if you remove that one, the repulsion between these electrons is much larger compared to removing that electron there, which is called the equatorial electron. These one are called axial electrons. So if we look at this structure right here, we see that we have 4 of these electrons that are still bonding pair, and then we have one that's just a lone pair on the central atom. So that one still is called trigonal bipyramidal in terms of its electron geometry, but the molecular geometry is called seesaw because it's shaped like a seesaw. It's like this is the base of the seesaw and this is the 2 seats where people can sit on it and go up and down like that. The example species for this would be SF4. If you remove 2 electrons on the equatorial position, now you just have this structure which looks like a T, so it is called a T-shaped molecular geometry. Again, same electron geometry, so trigonal bipyramidal. Here we have 3 bonding and 2 lone pairs. When you have remove 1 more, then all you have is this structure with the bonding. So that's called linear structure you would see if you have 2 pairs of bonding and 3 lone pairs. XEF2 would be an example of that. Make sure you pay attention to these angles that are given here because that's going to be important for the specific geometries that you have. So trigonal bipyramidal is always going to be 90, 120. Of course, there's a 180 here as well between those 3 atoms. And then depending on which one you have here, some of those angles will be maintained and some of those angles will not. We also have one more type of geometry that can be seen when we have expanded octet, and that's when we have 6 pairs of electrons. Looks like this. Here's your central atom. Here's 1, 2, 3, 4, 5, and 6. It's really very similar to trigonal bipyramidal, except that now your base forms a square in the middle. So if you want, you can call it square bipyramidal, but people don't call it that because that structure actually has a name in math, and that's called octahedral. So that structure will be called octahedral if all you have is 6 bonding pairs with 0 lone pairs. SF6 would be an example of this. If you start removing one of those bonding pair, and in this case, it doesn't really matter whether you remove the equatorial or the axial because they're all the same position. Actually, you can rotate this around and that atom can become this atom if you just kind of turn it this way. So there's no differentiation between the 6 different atoms, which is not the same when you have the trigonal bipyramidal structure. That one, there is a difference between these 2 positions. So in this case, since there's no difference, we remove the first one, then all you have left, if you imagine, is just the top part of this. And again, there's a square and then there's a pyramid, so we call that square pyramidal. So that'll be a 5 and 1 combination, 5 bonding, 1 lone pair. You can remove another one, and now all you have is just the square. It's on the same plane, so we call it square planar. Those are additional shapes that you have for the Lewis structures that can have expanded. Let's do an example on figuring out the VSEPR shape for specific species here that may or may not violate the octet rule or have multiple central atoms. So in this case, we are first looking at ICL4 minus, an ion. And if I draw the Lewis structure, it should look like this shown here. And to complete that drawing, because it's an ion, you need to put in brackets on the outside. Now, the way you determine the VSEPR structure is just by looking at the number of bonding and lone pairs around the central atom. So in this case, I have 4 bonding, and then I have those 2 lone pairs. It's an octahedral electron geometry. In the molecular geometry, that's going to be a square planar if you have 4 bonding and 2 lone pairs. Let's take a look at H2CO, the next species. The structure should look like the one shown here, and we have a double bond, but if you recall, a double bond is just one effective pair. So we have 3 bonding pairs around the central atom, resulting in a trigonal planar electron geometry. Since they're all bonding, that's also going to be the trigonal planar molecular geometry. Let's take a look at the last species, CH3NCO. Doing the Lewis structure gives you this structure here that satisfies octet and gives everybody a 0 formal charge. Ends up having 3 different central atoms. And so if you have multiple central atoms, you're going to have to determine the electron and molecular geometry for each of the central atom. I'm going to label those atoms 1, 2, and 3. And I'm going to set up a table where I figure out the electron and molecular geometry for each of the central atoms. If I look at carbon 1 has 4 bonds and no lone pairs. So that means that it's a tetrahedral carbon with 4 bonding, and then the molecular is also tetrahedral since all 4 are bonding. If I look at the nitrogen 1, remember that double bond counts as 1 effective pair, and then a lone pair. 3 pairs of electron is a trigonal planar electron geometry. You have a 2 bonding and 1 lone pair combination, which result in a bent molecular geometry. The last one is the third carbon. That one only has 2 bonds, 1 and 2. 2 means a linear electron geometry, and since they're both bonding, it's also a linear molecular geometry.